All right, welcome. We have our 20-2 lecture today, where we're really going to start to dig into some of the weird complexities that I talked about last time. So, kind of a refresher from last time, we started describing that we're trying to bridge together the macroscopic and microscopic realities. So, like a macroscopic description with a microscopic reality is how I should phrase that. We have the ideal gas law, we have these other factors, and these were empirically derived equations that describe most gases very well. Right? There's a couple little hiccups. There's a couple things that, the number's a little bit off or something like that. But for the most part, using the ideal gas equation, talking about the transformations between different states of a gas, it works very, very, very well. In reality now, we know that gases and other substances are all made of a bunch of constituent atoms, though. Right? All of these atoms that actually make up the whole system, one individual atom does not necessarily care about temperature. It doesn't necessarily care about volume or pressure. But the ensemble of them together seems to. So we started looking inwards and we tried to say, okay, let's look at these individual atoms. Let's look at some of the features of individual atoms and see if we can't tie these two descriptions together in some sort of way that we have one complete mesh between all of these. And last time we got to describing the mesh between temperature and pressure with our descriptions of individual atoms. And today we're going to dive a little bit more into specific heat. So if you remember, I've kind of thrown some random values at you so far with specific heats of different materials, and I've pointed out some similarities, but we haven't quite justified where all of those things come from. So kind of a review from last time. We know that the average energy per particle of a gas is going to be 3/2 kBt. If there's no internal structure, so this means a single monatomic atom floating around or anything else like that, right? That would be 3/2 kBt, and that works. If we wanted to find the total energy of an entire gas, right? So all of the billions and billions and billions of atoms that actually make up a gas, as we would describe it, then what we could do, this is just kind of a statistical thing. If you take the average energy times the total number of atoms, you get the total energy of the system. It's equivalent as if you had counted every single atom's individual energy and summed those all up together, right? It's exactly what an average does. So then, if we do something like that and we just plug in what we have found so far for the average energy per particle, then what we find is that the thermal energy of any gas is 3/2 in RT. Then we go back and we look and we think about, okay, well, I remember from before that the change of thermal energy is NCV delta T. And those look pretty close. The number of moles, that's the same. Delta T, it's a little bit different, but take E thermal final minus E thermal initial, and we can see where a delta T would show up there. Then that means, to marry these two descriptions, well, C of V has to be 3/2 R. And as long as C of V is equal to 3/2 R, these equations work, everything's justified, and everything works, right? And we're happy and everything's great. Let's check this real quick. Not related to C of V necessarily, but if I have a rigid container, so constant volume, right? And I've got a bunch of hydrogen gas mixed with a bunch of nitrogen gas, and they're all at the same temperature, right? They've been sitting together for a little while. They're in the same canister together. What statement would accurately describe the translational kinetic energies of each type of molecule? Think about it for a minute. I'm leaning towards B, and let's talk about why. We know that the average energy of a single particle would be 1/2 m VRMS squared. We can also describe it as 3/2 kBt, though, which says that as long as two gases have the exact same temperature, the average energy per particle is also equal. So if both of these gases are mixed together, if they're both sitting at 100 degrees Celsius, it stands to reason that the average energy per particle of both gases is equal. We're looking at B as the correct answer for this one. But what that means is that for something like hydrogen, in the case of hydrogen, the mass is much lower, so to compensate for that, the VRMS has to be a lot higher, right? And the other way, the nitrogen's a little bit heavier, so it doesn't need as much VRMS to actually reach that kinetic energy, but in both cases, the average kinetic energy per particle is still going to be the same. It's just that speed shifts relative to what the mass is, so that it's always set for a given temperature. So, let's talk about how this gets messy. Equipartition theory, and hopefully you've read about this by now, but equipartition theory essentially says that if I am adding thermal energy to some substance, then the thermal energy that I'm going to start adding is going to be divided amongst degrees of freedom. And we need to talk about what degrees of freedom really are, right? But for now, for every single degree of freedom, we get an additional 1/2 kBT. So, for our monatomic gas, it can go in the y-axis, it can go in the x-axis, it can go in the z-axis. 3 degrees of freedom, 3/2 R, 3/2 in kBT. And this is a little bit strange, and degrees of freedom are a little bit weird. And I need to kind of get into this. So, that's what we've got here, though, right? 3 degrees of possible motion, 3 dimensions that we can work through, and that gives us our 3/2 kBT. Now, this is kind of a cool thing, and I'm going to go off on a little bit of a quick tangent, but for two-dimensional particles, or particles that are confined to 2 dimensions for some reason, which are rare but are possible, if a particle is confined to 2 dimensions, then the specific heat of that particle will actually change in accordance with that. If it's not allowed to move in the z-axis, if it's limited to x and y, then the specific heat of that will only be 2/2, or 1, in RT, which is a really cool feature, right? But we talked about this last time that, okay, well, we can have motion in all 3 axes for most gases that we know, but there's other ways that we could have kinetic energy. There's other places we could put energy. For example, physics loves springs. We really do. We love oscillators, we love springs, we use it to describe everything, and for the most part, despite the fact that it's a little bit of a weird description to imagine a spring between 2 particles, it works incredibly well. It gives us very accurate values a lot of the time, and it makes describing a lot of our systems substantially easier. So when we're talking about something like a solid, we can more or less visualize this as I've got my atom, and it's allowed to jostle in any of the 3 axes. That's fine. But relative to the nearby atoms in the grid, I've also got some springs in the y direction, and I've got some springs in the x direction, and I've got some other springs in the z direction. And we can store energy in springs. Those are 3 additional degrees of freedom. And I realize this is a little bit kind of hand-wavy and strange, but really my justification for this one right now is going to be, well, look at the numbers. If it's supposed to be 3/2 kBT, or this molar specific heat is supposed to be 3R, then we're expecting something right around 25 joules per mole. And we go over to our table and we look, and it's not exact, but I've already kind of described this before. We get most of the way there. There are a lot of very, very fine complexities that make all of these things very different. There's internal structure to all of the atoms. There's a lot of weird things that can go on here. right? So we're not expecting necessarily to be exact. But there's an old saying that you can get 90% of the way there with 10% of the effort, and the last 10% of the way there to get to an exact solution is what takes 90% of the effort. And we don't need that extra 90% of the effort right now, right? Getting us most of the way there is what we've been doing with the ideal gas law and using a lot of these descriptions. And it gets us most of the way there. And for now, in this course, that's good enough. We get most of the way there to the proper description, to the proper numbers. So then we look at some of these other things, though, like ethyl and ice, and, well, those are a little bit weird. What's going on with those? Well, diatomic molecules are something. So reasonably, I can expect that this thing would also have my x, my y, and my z axes of freedom, right? Kinetic energy can be in x, y, and z directions, and that's all fine. But then we also talked about rotation, how that's a possibility. I could rotate around the x-axis, I could rotate around the y-axis, I could rotate around the z-axis. So that's 3 more. On top of that, there are also 2 modes of vibration by the fact that we have a spring. And this is a little bit weird at first. There's a couple different ways to describe how this is going. I've got 2 atoms attached by the spring, and that's why we're getting 2 modes from vibration in this one. It's not counted in exactly the same way we do with the solids, because in the case of the solids, we looked at 1 atom and then the springs, and then we didn't care what the springs were attached to. That was the problem for the next time. But in a case like this, we are considering the whole thing and the springs included, right? We're looking at the other side of what the spring is attached to. So there are 2 different degrees of freedom associated with this. The other way to view this as well is that relative to the other atom, right? If I hold 1 atom as my center of focus, then the other atom has a kinetic energy relative to this atom because of the spring, and a potential energy relative to this atom because of the spring. So that's another way that we can describe this, but whichever description you take, you're getting 2 more degrees of freedom from this, for a total of 8, or 4R. Which, if you've been looking ahead in the equation sheet, you'll see that's not quite what we get. So let me tear down one of these in the first place. And also, there's plenty of reading material down here at the bottom of the slide if you'd like to look at any of that stuff. I had a few words about this one, some of which I'm going through now. Imagine for a second, you have a perfect sphere. You don't put any marks on it or anything else. There's no nicks anywhere that would give it an identifier. You didn't take a Sharpie and draw an X on top or anything else like that. It's just a perfect sphere with no markings. Put a blindfold on, hand it to somebody, they spin it. They hand it back to you, you take the blindfold off. Can you tell that it's been rotated? Is there any indication that it could have been rotated? No. If they turn it 90 degrees this way, you can't tell. If they turn it 90 degrees this way, you can't tell. And it turns out that is a good way to actually tell if it's a degree of freedom or not. That rotation is indistinguishable. There's no difference to the atom if you spin it around one way or the other, right? Because it's still just a sphere. It didn't matter that I rotated it one way or the other or anything like that, because there's no association with that. So for a diatomic molecule, that is true for one direction. If I spin this thing long ways, imagine a cylinder. If I spin it along the axis of the cylinder, I can't tell the difference. Right? If I spin it 90 degrees one way or the other, or 180 degrees, there's no real difference. However, if I spin it around the other 2 axes, then clearly we can immediately see a difference. Right? If somebody rotated this around the y-axis or something like that and handed it back to me, I could tell. It would now be pointing towards me or something like that. And if you can tell that it's being rotated, it counts as a degree of freedom. So actually what we see here for diatomic molecules, I'll immediately mark one of these off. One of these degrees of rotation does not matter because it's indistinguishable. And as long as it's indistinguishable, there's not much I can do with it. Which is also why monatomic atoms, or monatomic gases, rather, monatomic gases don't have a rotation component because there's no spinning I can do that's meaningful. It doesn't matter if that single atom spins around because I can't tell the difference. And if I can't tell the difference, it's not a degree of freedom. So immediately, we revise this and we say, okay, well, one of these doesn't matter. But that would still mean I should find 7/2 R. And if you look at the equation sheet, that's still not it. C of P, the molar specific heat for constant pressure, is this value, but again, that one's a little bit different because there's some work being associated with that. We're looking for the C of V. So what's going on here? Well, as it turns out, equipartition theorem is actually kind of outdated. And it was outdated when it was made. There were some problems with it. As we studied diatomic gases more and more, equipartition was really neat because at first it does very well describe solids and it does very well describe monatomic gases. But the diatomic gases didn't work so well. And it got even stranger because the specific heat of a diatomic gas is not actually a constant value either. It goes through some pretty substantial changes. What's going on is that translational energy is the easiest place to put this energy. At low temperatures, when there's low thermal energy, so somewhere beneath 100 Kelvin or so, diatomic gases actually behave identically to monatomic gases. And keep in mind, this is not necessarily just kind of a theory predicting this. This is the empirical evidence of what we saw and what flew in the face of equipartition theorem, right? Equipartition theorem is still a useful theorem. We still use it to describe some things, but diatomic molecules immediately said, nope, right? It's not complete. It doesn't work. But we still use it because it does still have some use. So what we're really seeing here, though, is that when you're at low thermal energy, all of the energy is going into only 3 degrees of freedom. There's very little energy going into the rotation of atoms. Most of the energy is dedicated to just moving the atoms around. Once you reach a certain threshold, you start to see this increase into somewhere between 100 and 1000 Kelvin, where most of what we deal with is actually being done, right? We're kind of somewhere in the middle of this with most of our room temperature stuff and most of our heat engines. All of that stuff happens right here in this perfect middle region. In this middle region, diatomic gases have energy going into their translational motion as well as their rotational motion. The vibrational ones, making the atoms kind of buzz back and forth, that doesn't happen until you get much, much hotter, right? So if we actually were to deal with any gases at those temperatures, kind of getting into plasma range, really, then we would have to think about the vibrational modes, but there's kind of a word that it's frozen out in the meantime. Simply put, it's not an easy place to put a bunch of energy. The energy is more likely to go in these other 2 places, and there's some wacky stuff that plays into this, and you actually have to have quantum mechanics to finish describing this picture and what's going on with it. But it's kind of neat. This is all kind of playing into the history of how we struggled to deal with thermodynamics. A lot of thermodynamics was derived empirically, and then we were poking holes in that description that we made and saying, okay, well, this clearly isn't complete. But it's still useful because it was used to describe a lot of those things in the first place, so it can still be used to describe a lot of those things. Just occasionally, we have holes that we have to kind of try and fill one way or the other. So as long as we're in this middle region, though, we're expecting to see 5 useful degrees of freedom. That is to say, our molar specific heat, C of V, is 5 halves R. C of P would be 7 halves R, because C of P is always C of V plus R. And then our gamma value for those adiabatic expansions and compressions would be 7/5. So it's a little bit different. So let's go ahead and look at this next whiteboard problem. So let's imagine we have 3 different substances, right? I've got a monatomic gas, I've got a diatomic gas, I've got a solid. Liquids are a little bit funky. We're not going to talk about those. If I were to add 1 joule to 1 mole of each of these 3 substances, what kind of temperature change would I expect to see? So, again, we're going to assume all of this stuff is 100% completely ideal, no weird things going on or anything else like that, right? What that means is that what type of substance it is determines the specific heat. So for a monatomic gas, 3 degrees of freedom that are actually active. For a diatomic gas, 5 degrees of freedom that are actually active. For a solid, 6 degrees of freedom that are actually active, right? 6 halves. And with that, we've actually got most of the problem, because each of these, we're talking about a change of the thermal energy of 1 mole of the substance. So for all 3 of these, change, let me do that in black. Change of thermal energy is always equal to NCV delta T. We're looking for delta T, so let's rearrange this. Say delta T is equal to change of E thermal divided by NCV. And then we say, okay, well, delta E is 1, N is also 1. So really, every single one of these answers is delta T is equal to 1 over C of V. And when we plug those in, what we find is something like this, that the, whoops, I shouldn't do equals. Delta T for monatomic gases, something like 0.08 Kelvin, should be a very tiny amount. For the diatomic gas, it's 0.48 Kelvin. And finally, for the solid, it's not 0.48. Catch that before anybody else can call me on it. 0.048. And then finally 0.04 Kelvin. Thermal interactions, right? We had a picture similar to this way at the very beginning, right? When we basically said, okay, if I have object 1 at a certain temperature, and I have object 2 at a certain temperature, and I allow them to thermally interact, which really means I smash them together, right? One way or another. They can either touch, or I mix 2 gases together, or something like that. Heat is allowed to go back and forth between those 2. Then we said temperature is essentially something is higher temperature when heat travels from that into the other object. And that was, again, still a macroscopic description. Temperature and heat are macroscopic descriptions. But what we know about the entire thing is that the thermal energy of the system as a whole should be constant. It's insulated, and so the only change of energy is actually happening between these 2 objects, or between these 2 substances. And this was essentially the basis of our calorimetry lab, right? To say, okay, well, there's no heat exchange with the outside environment. All heat exchange, or all thermal energy exchange, is happening inside. Now, we are equipped to deal with the fact that there might be something done other than heat. There might also be work, right? But both of those are encompassed together if we talk about thermal energy. But we can look at this on the inside and we can say, okay, well, that was the macroscopic description. If I look at the microscopic description, what's going on there? A higher temperature object means that on average, all of the particles that make up that object have higher energy, right? On average, it's a big distribution of things, but on average, the particles of T1, because it's greater than T2, are going to be higher energy than T2. So anytime particles from each substance collide, particle from 1 is going to impart some additional energy to particle from 2, and they're going to get closer as a whole to being equal. Now, keep in mind, there are all sorts of collisions happening, and there are some very high-speed particles from container 2, and there are some very low-energy particles from container 1, and it's entirely possible that some of these collisions have energy going in the opposite direction. But as a whole, because the average particle has more energy on the side of T1, heat is going to flow from that side, right? If I'm scaling up everything, if I'm no longer looking at just every single one has a possibility that it goes the other direction, but if I sum up all of them, that is much less likely than energy going from T1 into T2. And that's going to continue happening until those averages meet. When the average particle from each one is exactly equivalent energy, there's no average energy to be imparted one way or the other, the temperatures will be equal. And so again, we kind of create this web of our macroscopic and our microscopic descriptions, temperature versus average energy of particles. All of it meshes together into this nice big web. So, taking something like this in mind, let's try this. Let's say I take 2 grams of helium, and I've got it at some initial temperature, 300 Kelvin. And I take 8 grams of oxygen at 600 Kelvin. I mix them together, right? So they're both at their own temperatures, and then I mix them together in one canister and shake it around a little bit or something like that, right? And I let them thermally interact until it's all just one final temperature. What is that final temperature going to be? There's a couple different ways that you can do this one. If you're fast with one of them, try the other. See if you can come up with 2 different ways that you could consider solving this one. Let's go ahead and start to take a look at this one. And as I kind of mentioned before, there's 2 different ways that we might consider doing this problem. I'm going to start with this with kind of a calorimetry approach, right? So one of the first things you're going to need to do, though, is you're going to need to convert these things. You need to find the number of moles of each gas, right? So you've got essentially the mass in kilograms. You need to convert that to a number of moles. So for example, helium here, if I'm just doing this kind of on the page, I've got 2 grams of helium. That means I would have 0.5 moles. If I have 8 grams of oxygen, that means I have 0.25 moles. And then we're set with those, right? So now those are values that we actually have given for us. Because I'm going to do a lot of this symbolically here. But anyways, the calorimetry approach basically says, okay, well, they're both going to go through some sort of change of thermal energy, but they're in the same canister together. It's well insulated. There's no heat exchange with the outside, which means that the total change of energy of the system, and actually I want to make that just a little bit more fine point so I can write this a little bit easier. So the total change of energy of the system, E thermal, but I'm going to rewrite this and say instead of E thermal, let's say change of E for the system. Right? We know it's all a bunch of thermal energy, so let's just make the subscripts useful for us. Total change of the energy of the system is going to be 0, and that is made up of the change of energy of the helium plus the change of energy of the oxygen. Okay, well, knowing that, then what we could do from here is say, all right, well, I'm going to have, for either of these, right, remember that change of thermal energy is still just going to be an N CV delta T. So what we can say is, let's start with the helium. N of helium. And it's a monatomic gas, so C of V is 3/2 R. Delta T, let's just go ahead and plug that in. T final minus T initial for the helium. And then remember, we're adding these two terms because the delta T's will take care of the positive and negative for us. So I'm going to do the exact same thing for oxygen, remembering that this is going to be a 5/2 R because it's a diatomic gas. T final minus T initial of the oxygen. Okay. Now, remember that we are solving out here for the final temperature. And if I look around at these, I say, okay, I know the number of moles of each gas, I know the initial temperature of each gas, and R is one of those values that we've had since chapter 18. So the only thing in this big equation that we don't actually know is T of F. Perfect. We're ready to solve. We've just got to do a little bit of rearranging, some redecorating on this equation to make it solvable. So I'm going to rearrange this and I'm going to say, okay, let's pull out all of the terms that have anything to do with TF. So TF times distributing in that polynomial times, actually, before I do that, let me take one more step and make this a little bit easier for myself. What's 0 times 2? Still 0. What's 0 divided by R? Still 0. But if I multiply by 2 and divide by R, I can cross that out of each term. And that just makes this a little bit easier to write. If you leave them in for the entire problem, it doesn't change the answer, but it's less terms to keep track of. But I'm left with a 3 and the 5. So I've got number of moles of helium times 3, and that's it for that one. And then I'm going to pull it from the oxygen as well. So that's number of moles of oxygen times 5. That's all my stuff times TF. And then I'm also going to have essentially the leftover terms, right? Minus number of moles of helium times 3 times T of helium. Move this over just a little bit more. Minus number of moles of oxygen times 5 times initial temperature of oxygen. All of this still equal to 0 on the left-hand side. So we can say, okay, well, I'm just rearranging for T of F. Take these terms and go ahead and move them over to the other side, and then divide all the stuff, multiply next to TF, and we've got our final answer. So I'm going to move that exponent to the outside, which as I start to plug this in, you might notice that this is essentially just a big weighted average. And we have essentially our final expression for what this temperature should be. I just need to plug in my values at this point, right? And at the very end, I should come out with a number that looks something like 436.4 Kelvin. So, somewhere right in between those two, right? So, that's method 1. Right? And that's kind of, you can see that there's like a retrospective a little bit on calorimetry in this, right? It's just how we solved all of our old calorimetry problems. Now the specific heat is just given by what type of substance it is, rather than looking it up on a table. Now, there's another way that we can still do this, right? And it's looking more about what we just saw on the slide right before this problem. So let's talk about method 2. The other method that I can imagine this is that instead of thinking about the change of thermal energy, I think about just the thermal energy as a whole. So the thermal energy of the system would be equal to all of the thermal energy of the helium plus all of the thermal energy of the oxygen. And still, as before, I know that there's no energy entering or leaving the system. So between my initial state and my final state with each gas, still the same total energy, right? That hasn't changed. So we can use our new fancy pants addition of thermal energy to say, okay, well then this should reasonably be The number of moles of helium times 3/2 R times the initial temperature of the helium, right? And it looks extremely similar to the change. It's really a pretty much identical equation. It's just delta T or regular T. Plus all of the thermal energy coming from the oxygen. So that is an N times 5/2 R times T of the oxygen. And that's fine. And that would come out to be some total energy, if you're looking for it, as 4,988.4 joules. That is the total energy in all of this gas right now, if you'd like to have that value. But then I can say, okay, well, this is, reasonably speaking, once they're at the same temperature at the very end, energy per particle's all going to be the same, or better yet, I can use the exact same equation to describe this again. But now, it's in H of E times 3/2 R times TF. That's the only difference. Maybe they've divvied up this energy a little bit more evenly, but I can use essentially the exact, TF. And it's still equal, right? This is my initial state, this is my final state, but the expression still applies. So if I do something like that, though, then I can say, okay, well, I know the initial temperature, I know the number of moles for each of these. The only thing that I don't know, again, is TF. So I can arrange this, and I can say, okay, well, then TF is just equal to the total system energy divided by, and is there a clean way to do this one? Trying to see, we'll just go with this for now. I'm sure I could rearrange this to look a little bit nicer, but this will work. And that's what we end up with. So we've got one last problem that we want to look at for today, and that'll be this one. So here's what we've got. Regular air temperature room, regular pressure, atmospheric conditions, 2x2x2 room. I have a 1 kilogram ball sitting in the middle of this room. It's some art installation or something. Atmospheric gas, for the most part, roughly speaking, say 78% nitrogen, 21% oxygen, and then 1% other things, but you know what? 80 and 20 is close enough. All diatomic, though. I want you to find a couple things. First, how much thermal energy is in the air in the room as a whole? And you can kind of assume that the ball doesn't make a big difference or anything else like that, but how much thermal energy is there in the room? And the second thing I want you to find is going to be, all right, let's say that we could convert some of that thermal energy and we could use it to lift the ball up by a meter. How much energy would it take? What's the difference in that energy? And then second, how much would the temperature of the room have to decrease to make that happen? Let's go ahead and start taking a look at least part A for this one. So we're looking at finding just the thermal energy of the air in the room. And I'm going to assume the ball is not big enough to really make a big difference, right? Unless this ball is like 1 meter diameter, it's not going to take up a substantial amount of space. And I can do this in a couple different ways. Again, like there's slight differences in the ways that you can do this one. But anyways, we're going to start with the same equation regardless. So E thermal is going to be equal to NCVT, right? We know that since we're dealing with a diatomic gas, this is going to turn into 5/2 R times T. And then I don't really want to calculate what the number of moles are. I'm just not feeling it right now. Instead, what I could do is I could do a little bit of tricky reworking and take the ideal gas equation and say, okay, well, in RT, I recognize that. That's just P times V. My pressure, standard atmospheric pressure, is 101,325 pascals. My volume, it's a 2 by 2 by 2 room, so it's a total of 8 cubic meters. I can just plug those two things in right here. And when I plug both of those in, I should find something actually really large, right? 2.026 times 10 to the 6th joules. Not a small amount of energy. Not at all. Right? Now I can also draw kind of a bad picture of what's supposed to happen here in part B, right? So I've got a 1 kilogram ball. I want to lift it up in the air because it started on the floor. Perfect. There we go. Sending out my applications to art school right now. But anyways, it started right here. No potential energy. And then we gave it some potential energy. We're saying, let's steal that potential energy from the energy of the room. Right? So basically what we'd be saying here is that the potential energy that this thing has now comes from the change of thermal energy. It's got a negative sign because I'm pulling it from one place, putting it into another. So that's kind of your hint to get started on part B if you haven't been working on it so far. So, and this is going to be a little bit weird at first. So what I'm going to do is I'm going to kind of set this up in such a way. So I'm going to say, okay, the potential energy is equal to the potential energy gained lifting this thing up into the air. Let's just go ahead and say it's the absolute value of the change of energy. And that might seem a little bit clunky at first. But like really what I'm just trying to do is I'm trying to make sure that there's not some weird negative sign floating around in here that makes it look confusing. So we're going to put that negative sign back in here, but let's just leave it like this for now. So, hopefully we all remember this. Gravitational potential energy, mgh, is equal to, and I'm just going to plug in for what we've got here, right? So the number of moles, C of V, times delta T. Okay? And in just the same way as before, we say, okay, well, I know it's a diatomic gas, so if it's a diatomic gas, then C of E is equal to 5/2 times R. And now I've got a personal vendetta against calculating lowercase n. If you have already calculated lowercase n, don't go through this extra step that I'm about to. Just plug it in now and find the answer, right? But what I'm going to do is I'm going to say I recognize nr is actually equal to, and here's my 5/2. The 5/2 doesn't come along for the ride. But nr is actually equal to P1V1 over T1. And this is a long, drawn-out way of not calculating the number of moles. But it means that I can put everything I have, all of my original variables, into one equation together. And then we said at the very end that we're solving out for delta T. So that's the thing that we're really after. Now, I'm going to put the minus sign back in. And I wanted to do it like this because I know the temperature has to go down, right? I'm pulling energy from the room and I'm putting it into potential energy of a ball. So I know the temperature is going to go down. So if you got to this step and you find some weird value, you know that the delta T has to be negative at the end. If you found a positive, turn it into a negative. But anyways, we know what the mass is. We know G is still 9.8. We know the height's 1 meter. We've got all of this other stuff that we've got. So really, at this point, we're ready to just say, okay, mgh times 2/5 times T1 over P1V1 is equal to negative delta T. Right? That's all a bunch of positive values, which is what I was saying from before. So we know that the actual delta T should be something like negative 0.00142 Kelvin. That's a really, really tiny amount. That's a really tiny amount. That's like a whoops, I opened the door and some air transferred between the room and the hallway. And it's going to be a substantially larger temperature change than this. Relative to the rest of the room, the energy that it takes to actually do this is tiny. Right? It's a really small amount that it's going to take to actually lift this ball up. So if it's such a small energy as compared to the total energy that's in the room right now, what's to stop this from happening? Why won't it happen? Physics would allow this. This is not something that's unfeasible. There's no mystery equation that I'm not showing you. This is a possibility. That's on the right track. Think about what it takes to actually cause this to happen. You know, assuming, again, that I'm not the one physically lifting up the ball, I'm watching from a window or something like that. The only thing there that could actually do the work to lift this thing up is going to be the air molecules. How are they going to do that? I'm going to take a chance and say that it's probably not one really, really fast particle, because that momentum difference is probably going to be something in the relativistic speeds, and relativistic momentum's nasty. And also, you know, the room would you would see sparks shooting. So it's not that one particle goes really, really fast and makes it happen. Instead, assuming that all of the particles are roughly somewhere around that average thermal energy, what you'd have to have is, well, suddenly all of these collisions would have to be happening on the bottom of the ball, and comparatively speaking, it would have to be a lot more collisions than would be happening on the top. And if anybody's actually calculated out the number of particles that are in this room, I don't have an exact number here. It's on the order of 10 to the 25th, 10 to the 26th. It's not a small number of particles. And these are pretty tightly packed. Remember what we calculated from before about the mean free path? How far can a particle go until it runs into something else? And we did that with roughly air conditions, right? Room conditions. And we said, okay, about 10 to the negative 7th of a meter. So the number of collisions happening on the ball at any given moment are billions of collisions. And to think that you would have to have, so, and they're coming from every single direction, right? We talked about this last time a little bit, that, you know, why don't I feel any net force? And it came from two things. For one, the relative size of the atoms compared to my size means that momentum difference, I'm not going to feel it, right? I'm not going to say barely feel it. I'm not going to feel it. So many orders of magnitude difference between my mass and the mass of a single air particle that there's no way that I'm actually going to feel it. But on top of that, it's the fact that all of these collisions are happening from every side, and the net force on me at any given moment is going to be zero. Or it's going to be so incredibly small, so very nearly zero, that, you know, it's kind of this tiny buzzing up and down to the point that I would never ever feel that. So just in the same way here, you have to imagine what's the likelihood that, for whatever reason, there were hardly any collisions on the top, but there's suddenly a lot of collisions on the bottom, and it carries up by 1 meter. It's possible, because this motion is random. It's possible. But I'm willing to bet that the heat death of the universe is going to come before this happens. I would make that bet. And that's kind of the fun part of thermodynamics, is that thermodynamics is oftentimes just the statistics of matter. Right? Quantum mechanics, it was born from a few different things, but part of it was born from the statistical nature of thermodynamics. And it's kind of a neat thing, I think. And it shows up in a few different places. And like stuff like this, some events do happen, right? I'm not going to say that this could never possibly happen. Once again, physics would allow this to happen. There's no written rule that says that it's impossible, but the likelihood of it is so incredibly small that I doubt anyone would ever see it. It's kind of like something similar along the lines to quantum tunneling. Quantum tunneling is a real thing. It's not just a buzzword or anything else like that. Electron microscopes work by tunneling electrons from a sample up to a tiny, tiny atoms thick gold needle, and that's what actually images what you're looking at. It's a really cool thing, actually. And for certain electron microscopes, you have to make your own needle, and that's awful. But that's a circumstance where the particles are very small and the barrier is very small and the tunneling is very possible. I used to have jokes with one of my science teachers about, for a lab activity for the class, everybody goes outside with a soccer ball and kicks it against a brick wall for an hour, and we see if anybody can tunnel it through. It's possible, but that likelihood, again, is so incredibly small that we will never ever see it. You would see anything happen technically, but the likelihood is just nothing. And that's back onto my tangent, though. That's kind of like, I think one of the misconceptions with quantum mechanics and thermodynamics and these things is that, yes, these things are technically possible, but the likelihood is so incredibly small that it's never going to happen. Events have to be a small enough change of energy or over a small enough distance to ever even consider seeing the chance, to ever even consider a 0.000001% chance. That's something that I would consider would be possible and we might see, but these things have so many zeros before that one that it's never going to come up. But anyways, I think that's the end of our 20-2 lecture.